Here is our uniform cylinder of radius 10 centimeters and mass 20 kilograms. We're going to rotate it about an axis 5 centimeters offset from its center of mass. So that's drawn with this X here. So it's going to rotate about that point like a wobbly tire. What is its moment of inertia about that point? So of course we're going to use the parallel axis theorem. Here's the center of mass axis. So our H value for the parallel axis theorem is 5 centimeters. So you see in our equation for parallel axis theorem, there's 5 centimeters for H. And then the moment of inertia for a uniform cylinder through its center of mass is 1/2 mr squared. So I can plug in all the numbers and see that my moment of inertia has a value of 0.15 kilogram meters squared when rotating through that axis. If the cylinder is released with its center of mass at the same height as the axis of rotation, this center of mass will swing down to this point. When it reaches that lowest spot, how fast will it be rotating? So we're going to use conservation of energy that says potential plus kinetic at some beginning time point is the same as potential plus kinetic at some later time point. So initially it starts from rest, so my kinetic energy is 0, and it only has gravitational potential energy of mgh, where h you see is the height difference from this location to this location is that offset distance of 5 centimeters. And then when it reaches the lowest point, since we consider that to be our reference point with 0 potential energy at the lowest point, my potential is 0 and my kinetic is 1/2 I omega squared. My value for I found it up here in part A, and now I can solve this equation for omega. And there's the calculation, 11.4 radians per second.